Welcome to Podcast Learn and Fun. Let's start today's journey of learning. We often talk about things moving in straight lines, like a rocket blasting off, or, a sprinter racing on a track. But what about when things spin? That's where things get really interesting. We have to start thinking about angular momentum. It's this fascinating concept that's all about how things rotate. Think of it like the spinny cousin of linear momentum, the one we use to describe motion in a straight line. And just like linear momentum, angular momentum is a vector, which means it has both a magnitude, how much oomph the spin has, and a direction.
And to figure out that direction, we can use something called the right-hand rule. It might seem a bit quirky, but it's a handy trick. To visualize the direction of the angular momentum, imagine you're holding a spinning basketball with your fingers curled in the direction it's spinning, your outstretched thumb. That points in the direction of the angular momentum vector.
Okay, so let's unpack this a bit. Angular momentum is about how much spin something has. And we can figure out the direction of that spin using the right-hand rule. Got it. But what affects how much angular momentum an object has?
Well, several factors come into play. One is the object's linear momentum, how fast it's moving in a straight line. Another is the distance from the axis of rotation, the imaginary line around which the object is spinning. And finally, the angle between the object's position and its linear momentum also plays a role.
Okay, I think I'm following so far. So the faster something's moving and the further away it is from that axis of rotation, the more angular momentum it has.
That's the general idea. Think of a figure skater doing a spin. When they pull their arms in, they spin faster, right? That's because they've decreased their distance from the axis of rotation. But here's the kicker. The total angular momentum stays the same.
Wait, what? How does that work?
That's where the concept of conservation of angular momentum comes in. It's one of the fundamental principles in physics. Basically, in a closed system, where there are no external forces acting on it, the total angular momentum remains constant. So when the skater pulls their arms in, their moment of inertia decreases, but to compensate, their angular velocity increases.
Okay, this is blowing my mind a bit. So even though the skater is spinning faster, the overall spin energy is staying the same.
Exactly. It's like trading one form of rotational energy for another. And it's not just figure skaters. This principle applies to everything, from spinning tops to planets orbiting stars.
Wow. Okay. So we've got linear momentum, angular momentum, the right-hand rule, and this conservation principle. It's starting to feel like we're building a whole toolkit for understanding how things spin. But there's one term I keep hearing that I'm not quite clear on, moment of inertia. What exactly is that, and how does it fit into all of this?
That's a great question. The moment of inertia is essentially the rotational equivalent of mass. It tells us how resistant an object is to changes in its rotation.
Okay, so a heavier object would have a larger moment of inertia.
It's not just about the weight, but also how that mass is distributed relative to the axis of rotation. Imagine you have a spinning top. If most of the weight is concentrated near the tip, it spins easily. But if the weight is spread out further from the axis, it's much harder to get it spinning and keep it going.
Ah, I see. So the shape and mass distribution really matter, like a solid disc and a thin rod.
Yeah.
Even if they have the same mass, would have different moments of inertia because their mass is spread out differently.
Precisely, and that's why they spin differently. Even if you apply the same force, the moment of inertia directly affects the angular momentum. For a rigid object, its angular momentum is determined by its moment of inertia and how fast it's spinning, which we call angular velocity.
So an object with a higher moment of inertia, like our spinning top with its weight spread out, will spin slower at the same angular velocity compared to an object with a lower moment of inertia.
Exactly. It's all about how that mass is distributed.
This is making more sense now. So we've got the object's linear momentum, its distance from the axis of rotation, and now we're adding in the moment of inertia. It's like we're layering on these different factors to get a complete picture of how things spin. But one question keeps popping into my head. How do we get things spinning in the first place? Like, what causes a change in angular momentum?
You're talking about torque. Think of it like the rotational equivalent of force. It's the push or pull that causes an object to rotate or change its rotational speed.
Yeah, I'm starting to see the connection here. So just like a force can change an object's linear momentum, a torque can change its angular momentum.
Exactly. It's all about applying a force at a distance from the axis of rotation. Think about pushing a merry-go-round. The harder you push, and the further out from the center you apply that force, the greater the torque, and the faster the merry-go-round spins.
It's like the force is amplified the further out you push. So Torque is what gets things spinning, but what determines how quickly the spin changes?
That's where angular acceleration comes in. It measures how fast the rotation speeds up or slows down. Torque is directly related to both the moment of inertia and the angular acceleration. Just like pushing a swing harder makes it go higher and faster, applying more torque to an object with a lower moment of inertia will result in faster angular acceleration.
This is all starting to click. So to sum it up, we've got angular momentum, this measure of an object's spin. And it's determined by things like the object's linear momentum, its distance from the axis of rotation, and its moment of inertia. And to change that angular momentum, we need to apply a torque.
That's a great summary. And remember, the concept of conservation of angular momentum is key. It tells us that in a system without external influences, the total angular momentum stays constant.
Right, like our figure skater, pulling their arms in to spin faster.
Yeah.
They're not magically creating more spin, they're just redistributing it to keep that total angular momentum constant.
Absolutely. It's a principle that applies to everything, from the smallest particles to the largest galaxies. Understanding these concepts is crucial for analyzing any rotating system. From the simple spinning toys we played with as children to the complex movements of celestial bodies.
Wow, it's amazing how something as simple as spinning can be so complex and yet so fundamental to our understanding of the universe. We've covered a lot of ground today. It feels like we've just scratched the surface of this fascinating topic, and I'm already eager to dive deeper.
There's always more to explore. But for now, I think it's time to give our listeners a chance to digest all this amazing information they might need to spin around a few times themselves to let it all sink in.
Ah, good one.
It's incredible how much physics is packed into something as simple as spinning, isn't it? And what's even more fascinating is that this concept of angular momentum, it pops up in all sorts of unexpected places.
You know, when we were talking about the conservation of angular momentum, the example of the figure skater made sense, but I'm curious about how this principle plays out in other real-world scenarios. What are some other examples where angular momentum is at work?
Oh, there are countless examples. Let's take a look at something we encounter every day. Bicycles. Have you ever noticed how much easier it is to balance a bike when it's moving than when it's stationary?
Oh yeah, definitely. It's almost impossible to stay upright when you're completely still.
Exactly. And that's largely due to the angular momentum of the spinning wheels. Those spinning wheels act like gyroscopes, resisting changes in their orientation. That inherent stability they provide makes balancing much easier when the bike is in motion.
That makes so much sense. It's like the spinning wheels want to keep spinning in the same direction, which helps keep the bike upright. It's similar to how a spinning top stays upright until it loses its momentum, right?
Precisely. The same principle is at work with spinning tops, gyroscopes, and even the Earth itself. The Earth's rotation gives it a significant amount of angular momentum, which helps stabilize its axis of rotation over long periods.
So without that angular momentum, the Earth would wobble much more dramatically. That's a pretty wild thought.
It is, and it highlights how crucial angular momentum is for maintaining stability and predictability, not just here on Earth, but throughout the universe. Without it, things would be a lot more chaotic.
I'm starting to see angular momentum everywhere now. From the way a frisbee flies to the way a helicopter stays airborne, it's all connected to this fundamental concept.
It's like having a secret decoder ring for understanding the universe. Once you start recognizing these underlying principles, the world becomes a much richer and more fascinating place.
Okay, so we've talked about bicycles, tops, and even the Earth. Are there any other surprising examples where angular momentum plays a crucial role that might not be so obvious?
Let's consider something completely different. A rifle. Have you ever wondered why rifles have those spiral grooves called rifling inside the barrel?
I have. I know it has something to do with accuracy, but I've never understood exactly how it works.
Well, those grooves are there to impart a spin to the bullet as it travels down the barrel. And guess what? That spin gives the bullet angular momentum, which, as we've seen with the bike wheels, helps stabilize its flight path and increase its accuracy.
So by spinning the bullet, it's less likely to tumble end over end as it travels through the air, which would cause it to veer off course.
Exactly. The spin keeps the bullet pointing in the right direction, ensuring a straighter trajectory and making it much more likely to hit its target.
That's incredible. It's like a tiny gyroscope flying through the air. I never would have guessed that something as seemingly simple as a spiral groove could have such a significant impact on a bullet's accuracy.
It's a testament to the power of physics and how understanding even seemingly abstract concepts can lead to practical solutions for real-world problems.
It makes you wonder How many other everyday inventions rely on angular momentum in ways we don't even realize?
Countless, I'm sure. From the wheels of our cars to the turbines that generate electricity, angular momentum is at work all around us.
So the next time I see a spinning object, whether it's a basketball, a bicycle wheel, or even just a fidget spinner, I'll have a newfound appreciation for the intricate physics at play.
And you'll be able to connect those everyday observations to those granular examples we've been talking about, like planets orbiting stars or even the behavior of subatomic particles. It's all part of this fascinating web of interconnectedness.
You know, we've talked a lot about how angular momentum affects the motion of objects, but there's one aspect we haven't touched on yet, something called precession. Have you ever noticed how a spinning top doesn't just spin perfectly upright? It kind of wobbles in the circular path?
Ah, yes. Precession. It's a captivating phenomenon. It happens when the axis of rotation of a spinning object itself rotates. In the case of a spinning top, gravity is pulling down on it, creating a torque that causes its axis of rotation to slowly trace out a cone shape.
So it's like the spinning top is drawing a circle with its axis as it spins.
Precisely. And this precession effect isn't limited to spinning tops. It's seen in gyroscopes, the Earth itself, and even the behavior of subatomic particles.
Wait, the Earth precesses too. What does that even mean on a planetary scale?
It means that the Earth's axis of rotation isn't fixed in space. It slowly wobbles like a giant top, completing one full precession cycle roughly every 26,000 years.
26,000 years? That's almost unimaginable. What causes the Earth to precess like that?
It's mainly due to the gravitational pull of the sun and the moon on the Earth. You see, the Earth isn't perfectly spherical. It bulges slightly at the equator. That bulge, combined with the gravitational forces from the sun and moon, creates a torque on the Earth, causing its axis to slowly precess over time.
So the Earth is doing this slow motion wobble over thousands of years. That's mind-blowing. Does this precession have any noticeable effects?
It certainly does. One of the most interesting consequences is that it gradually shifts the position of the stars in the night sky. The constellations we see today wouldn't have looked the same to ancient civilizations thousands of years ago.
Although the positions of the stars would have been different due to the Earth's wobble.
Exactly. Over that 26,000-year precession cycle, the North Star actually changes. The star we currently call Polaris won't always be the North Star. It's like the Earth's slow wobble is rewriting the map of the stars over incredibly long periods of time.
This whole conversation about precession has opened up a whole new layer of complexity and wonder to the concept of angular momentum.
And it highlights how even seemingly simple phenomena can have profound implications when we dig a little deeper into the underlying physics.
I feel like we've only just scratched the surface of this topic. You know, it's incredible how something as seemingly simple as spinning can lead to such complex and profound consequences. It makes you wonder what other hidden wonders are waiting to be discovered out there in the world of physics.
Absolutely. The more we delve into the universe, the more we realize how much we still don't know. But that's what makes science so captivating. There's always something new to learn, something new to challenge our understanding.
It truly is an endless frontier of knowledge. And angular momentum, with its intricate dance of spin, torque, and precession, is a perfect example of how much beauty and wonder can be found in the fundamental laws that govern our universe. We've covered a lot of ground today. From the basic definition of angular momentum to its conservation principle, its real-world applications, and even its role in the quantum realm and the precession of celestial bodies. I hope this exploration has sparked your curiosity and inspired you to look at the world with a newfound appreciation for the intricate physics that surround us. Thank you for listening to Podcast Learn and Fun. If you like our videos, please subscribe, click the like button, comment, and share. See you next time.